Okay, quickly, here lossless loaded line. So here I've taken the transmission line of VZ, VZ and IZ. Voltage and current at any point of the transmission line. This is my load. Okay, ZL. And I have some Z0 and beta. I've taken Z axis from here 0 to minus L. So I've written that V and I here like this. V of Z equals to that V0 plus e power minus comma Z and V0 minus e power plus comma Z. And current also same. So this is V0 plus, sorry, this 1 by Z0 e power minus comma Z minus V0 minus e power plus comma Z. Okay, so what I'm going to do here is I'm going to put the Z equal to 0 at load. So this is I'm applying a boundary condition at load. Okay, applying boundary condition. This is one of the key steps. Okay, so I've taken such a way that the transmission line is placed on Z axis and the load is placed on exactly at origin, and and I am having a transmission line of length is L. Okay, I'm taking this length there. So what about the source? The source will have some value and impedance will be there. The source impedance, okay, is that G. This is all there, but I'm going to consider from the load point of view. Okay, because the load is something again I should know what kind of load it is and how this is going to influence my the voltage and current. Okay, so at load I am going to apply the boundary condition. So when I apply the boundary condition means what is Z value at load. So at Z equal to 0 we have a load. Our load is placed on origin. Z equal to 0. So in that case I can rewrite this for 1 and 2 as V of 0 as V0 plus and this is V0 minus. Okay, and I of 0 as 1 by Z0 times of V0 plus and minus V0 minus. Okay, so here what I have to do is I'm going to introduce can I write it like this, for example, what is the voltage at the load is the VR 0 is I of 0. So if I divide this 3 and 4, okay, so voltage at load, that is V of 0, and current across the load, that is I of 0. Okay, so what I'm going to do is I'm going to divide this to V of 0 by I of 0, that is voltage by current. I'll get the load impedance. Okay, so what I'm going to do is here the topic of seeing this derivation is the lossless line. So since it's a lossless, the comma is written as beta because alpha equal to 0 and the load is connected, so it's called a loaded lossless line or lossless loaded line. Okay, so when I apply the boundary condition at Z equal to 0, why I've taken this, there is some reason for it, we will see it later. So basically I could have taken Z equal to 0 to L, but I've taken in the opposite because the simplification will be easier. So when I put Z equal to 0, the first equation becomes V0 plus and V0 minus. The second equation becomes 1 by Z0 1 by Z0 over and V0 plus and minus V0 minus. Okay, so when I divide this voltage and current at load, I will get the load impedance, which is equals to 3 by 4. Okay, 3 and 4 the equation, that is nothing but V0 plus V0 minus and V0 plus minus V0 minus and Z0. Okay, so here I can write ZL by Z0 is nothing but V0 plus and V0 minus and V0 plus minus V0 minus. So what is this equation tells us? If I divide this load by characteristics impedance, okay, I will get the superposition of this incident and reflected voltage divided by the difference of incident and reflected voltage. That is my difference between the load and characteristics impedance. Then the mathematics, there is one formula is that if you recall it. There is a by b. If so, all are with me. I think it's not boring because it's a derivation. Okay, I know it is something like you have to substitute and here and there, but why we are doing and what we are doing, and if it is that is clear, then I think derivations no problem. Okay, I told also in the one of the class that derivations help us to understand the more concepts. Okay, and also you can think about in a different perspective. So what could be the kind of no practical issues will come while no doing the derivations. Okay, so this is I've taken a very typical the line. Okay, I've taken this for example, you can take this setup box sitting here. Setup box, it's need TV. Okay, you have TV and setup box is connected with that. Okay, that is your load is at. Okay, this is the antenna from rooftop. DTH antenna is there, so it is connected to the cable, coaxial cable. Okay, it's connected to the setup box. It's like a one of the transmission line example. You are connected some cable length, so that is a transmission line. So I'm going to find out, so what is that the voltage and current at setup box. From knowing that, I can find out the impedance of the load, or through the load I can find out the voltage and current at the load point. Okay, if I do that, I can find one important quantity, that what we are going to see it now by applying this mathematical formula. If a by b equal to c by d, then can I write like this? Whether is it correct or wrong, you can just tell me. A minus b, c minus d is c plus d. Okay, so if any fraction, two fractions are equal, a by b equal to c by d, so I can write a plus b minus a minus b, or a minus b by a plus b equals to c minus d divided by c plus d. Okay, can I write like this? So if it is correct, I can, same thing I'm going to write it, this equation also. So these kind of equations, we use it some no, occasionally in some places while solving the problem. Okay, so quickly, if I apply this formula, can I write like this? Come on, this has to move. Okay, can I write ZL minus Z naught, ZL plus Z naught, which is equals to V naught plus and plus V naught minus, again minus V naught plus, again minus V naught minus. Is that correct? I'm going to take this B minus C, sorry, C minus D. This is my C, this is minus D. So this is C, V naught plus and V naught minus, minus V naught minus, again this is a plus, correct? Minus V naught plus, this is a plus. Okay, so second time what I have to do is C plus D, just add these two, that this V naught plus V naught minus, V naught plus minus V naught minus, so add these two. Okay, so this is V naught plus and V naught minus, and plus V naught minus, sorry, V naught plus minus V naught minus. Okay, is that clear? Correct? This is my C, this is my D, this is my C, this is my D, I think. Okay, so what I can do is I can cancel out the terms. So what it will be cancelled out is this, everything will be cancelled out. No, this will be cancelled out. Okay, the numerator and denominator, this will be cancelled out. So how I can write it? So ZL minus Z naught by ZL plus Z naught is equals to V naught 2 V naught minus by 2 V naught plus. So I can cancel out this. So this is minus V naught minus by V naught plus. Again, we are transmission line is, it is fond of constants. Okay, and what you say, key parameters. Okay, so here I'm going to introduce one more key parameters, that is a reflection coefficient. Okay, so the reflection coefficients I'm going to introduce, that is a gamma. Keep it in mind, this is very, again it is one of unique parameters which is used not only in the transmission line, we will use it in the oscilloscope we call as a network analyzer. So that is the quantity of important is gamma. Reflection coefficient is nothing but V naught minus by V naught plus, which is nothing but ZL minus Z naught by ZL plus ZL minus Z naught divided by ZL plus Z naught. So the quantity of importance is gamma here. So what is that so important for that? So it will tell me if I have some kind of, I told there's a water dam and water is flowing onto the canal to the pipe, no, if there is any disturbance it will start reflecting back. So in the transmission line I don't want this reflection. I'll try to remove all the blocks in the canal and stones, so which is blocking the pathway of the water, right? So similarly this quantitative measure how much is reflection is happening, no, that I can measure by using this quantity of gamma. So you can closely, if you observe, this is the ratio of the reflected voltage or reflected wave voltage, that is more specific, okay, or reflected voltage wave, okay, reflected voltage wave divided by incident voltage. Okay, so ideal case, no, if there is no reflection, whatever dam is releasing water is reaching all irrigation center, there is no absolutely no reflection, right? So I'll get V naught minus is 0. So the quantity of gamma becomes 0. Okay, if gamma equal to 0, it's a perfect transmission line, there is no reflection. But if in practical case it may not be equal to 0, sometimes it may go to greater than 0. Okay, what is that maximum value it can go? Okay, so whether less than 0, is it possible? That also we can have to see what is that value it should be, what is the range of the value. So if you take the passive devices, okay, if you give the input, for example passive devices, I mean to say here is a filter or alternators, the output always will be less than or equal to input. That is a passive devices, no, like a diode, or if you take a resistor, if you take a inductor, the voltage what you give, the energy what you give, so it will be always less in the output, because there will be some losses in the device. Okay, so what is active devices? If you take a transistor, amplifiers, so that are active devices. If you take a passive devices, the output voltage we call here as V naught minus. Okay, the input voltage is V naught plus. So the output voltage always will be less than input voltage. So when you take the ratio V naught minus by V naught plus, this is numerator is always less than the denominator. So it will be always less than 1. So for passive devices, normal transmission line, passive devices is also normal transmission line, the maximum value we will get either this V naught minus can be equals to V naught plus. If you send 1 voltage, maybe I will get 1 voltage or less than that. Okay, or 0.8, 0.9 or 0.5. So the output will be always less than the input, or sometime equals to the input. Okay, so that case I may get this ratio V naught minus by V naught plus less than or equals to 1. Sometimes no output also. So the gamma value, especially the mod gamma can be a complex number. Okay, because ZL can be complex, Z0 can be complex. Now ideally I wants to real value, but practically the load can be sometimes complex. Okay, so gamma can be a complex number. If you take a magnitude of the complex number, if I find the value, the range will come between 0 to 1. So the reflection coefficients value, the normally typically will come between 0 to 1. Okay, so this is one of the quantity of importance is reflection. How much reflection happens? Okay, let us go with some small problem here, just to understand the reflection. Let us take a very good antenna. Let us take some practical antenna. Probably I'll take a Wlan antenna, which is there in the laptop, right? So I'll just, if you open the chip, there will be kind of antenna. It is printed. This is a Wlan antenna. Okay. Fine. So all the antenna, the standard impedance is 50. I'll take this 2 point, I'm feeding that power, it's a 50 ohms. Okay, standard impedance. While connecting from power amplifier, let us take, let us take power amplifier I'm giving to the antenna, so the power will be radiating to the, usually it's 2.4 or 5 gigahertz bandwidth. So it is radiating the power. Let us take some power, it is radiating. So power amplifier job is it will amplify the power in terms of milliwatts, from microwatts or nanowatts to milliwatts. Okay, watts it cannot do, that is little more power it cannot do. So the milliwatts power, and that's the guidelines, so it cannot emit more power. So let us take the milliwatts power is emitted here. So what is ideal characteristic of the amplifier? The input impedance should be high, okay, and output impedance should be low, correct, no? So let us take the input impedance is 1 mega ohm, so output impedance is, so let us take very small, let us take 100 ohms, okay. So this is some design values, no, power amplifier. Can you think about this problem? Because the amplifier is supposed to have a different input and output impedance, but when it connects to the antennas through the transmission line, the impedance has to be matched to the 50 ohms. If it is not matched, let us find out this gamma. Okay, so what is the load here? The antenna load is 50 ohms. Okay, and is that not characteristics impedance of the line? Supposed to be 50, but here I'm getting 100 ohms. Okay, so if you put this value, so what is this gamma you will get? So ZL is 50 minus Z naught is 100, and ZL is 50 and Z naught is 100. So this is minus 50 by 150, you get 1 by 3. This is point, how much? 3, 3, 3 is a 9, again 10 and 3, okay, 0.33 minus. So if you take a mod gamma is 0.33. So it's supposed to be 0, but it is not 0 because the impedance mismatch. So the reflection happening 0.33. So if you take 75, let us take, and what is the gamma? So 75 minus 50, sorry, I should be reverse, no, 50 minus 75. Okay, this is a load 50 plus line impedance is 75. So minus 25 by, this is 125, this is minus 1 by 4, this is minus 0.125. Oh no, so how much it is? 0.25, no? Okay, so this is minus 0.25, so mod gamma is 0.25. So which is better, 0.33 or 0.25? This is better because it's close to 0, because the impedance of 75 is close to 50 compared to 100 is compared to 50, correct? So the impedance, how much is varying, I can find out by using this gamma. This is very important quantity. So how much the variation of the impedance in the transmission line, I can find out by using the gamma. Okay, so here again the question is not fully answered. This power amplifier, this is my antenna. Okay, antenna symbol is this. Okay, this is my power amplifier. So this is 1 mega, this is my 100 ohms. Okay, this is my 50 ohms. So there is a problem actually, the impedance mismatch. So what I have to do is, in the circuits, microwave circuits, RF circuits, and you know, uh, printed circuits, or discrete circuits. So we use that, in often we'll use that impedance transformation. Okay, I'll use that impedance transformation circuit such a way that the impedance will be changed. Now when it is reaching to antenna, the 100 ohms impedance will be transformed to the 50 ohms. Okay, that is one of the reason we'll use this impedance transformation circuit, so that there is no any reflection. Okay, I think it is at 10 o'clock, and I think you have another class. So with that I will stop. I think I've covered little, and this continuation of the derivations all the way to find out the input impedance, we will see it in the next class. This input impedance on equations we will get, so that with related with the gamma, that is one of founding equations to go for a Smith chart. Okay, so this Smith chart is especially based on this gamma value. So That the reasons gamma is so important for a transmission line in RF circuits. Okay. So with that I'll stop and take care, and I'll see you in next class. Okay. Bye.